Alright, so it's time for the capacity test of these EVE 280 amp hour lithium iron phosphate batteries. In the last video we have the BMS installed. We're using a Batrium Watchmon core with the K9. So in this video we're going to connect an AC charger, let it charge up and balance a little bit. It should be mostly balanced because we did parallel these cells several months ago and balanced them manually. However, I did note when I connected the BMS that two of the cell groupings were lower than the rest. So hopefully that was just a bad connection when I had the balance leads connected, and we'll be able to balance them out here and proceed with our tests. So I will be using a similar setup to most of my other capacity test videos. I'm going to connect the standard silicone cable with 175 amp Anderson plugs, just because I already have that set up ready to go. Alright, so this morning I went through every one of these nuts and torqued them down with a torque wrench. I ended up going with 40 inch-pounds to start, but if any of you guys have a bank of these EVE batteries running, I'd be very curious to hear what torque specs you guys used. So this terminal here is the main positive of the battery pack, so I can attach the positive lead. And then I'll use my insulated torque wrench just to get this down to 40 inch-pounds. Okay. Alright, so I just want to double check that I have the correct voltage and polarity here at the main Anderson plug. 54.3 volts, and the wires are in the correct position, so we're good to proceed. So I'm just going to stick the Batrium shunt block right here temporarily for the purpose of this test. So the left side here is the battery input. Can go ahead and connect that now. And then I have a small wire that comes off the voltage sense pin here on the right. Goes to this alligator clip. This wire should be fused. I don't have a fuse on it, so if you're doing something like this, please make sure you put a fuse on yours. So the shunt data cable plugs into the side of the shunt, which will then feed back to the Batrium. And that will plug in the left side here where this yellow connection is. This is the 4-pin shunt connection. Just plug it in like so. Alright, so now we have a red LED flashing on the shunt block, and that indicates that it is receiving power. However, you'll notice that the green transmit and receive light is not flashing. So we need to go into the Batrium software and configure the Watchmon for this shunt block. Okay, so I'm in the Batrium software here. I'm going to click on Menu and go to Hardware. I'm going to select the Shunt tab and click Edit. Under the Type drop down here, you'll have a number of shunt options, various things that Batrium has sold in the past or sells currently. The shunt I'm using for this test is a Shuntmon 2 500 amp shunt block, and my nominal capacity 560 amp hours because I have two parallel of 280 amp hour batteries, so that comes out to 560. So I'm going to go ahead and click Save, back to Menu and Chart. And now that we entered our shunt settings, we can see the shunt is reporting 54.50 volts. Additionally, we can now see the green transmit receive light blinking on the Shuntmon. Alright, so for charging this battery, I'm going to use this Battery Evo power supply that I purchased from Big Battery. And this is rated for 17 amps, though I've seen it push more towards 18 or 19 at 58.8 volts. So that will put the batteries right around 3.67 volts per cell, which is 0.02 volts over what their rating is. However, I think that will actually give the BMS a great opportunity to balance these cells out before our discharge test. And since this is an Anderson 50 amp connector, I've got this little cable I made up here with a 50 and a 175 amp, along with a very cheap basic circuit breaker just for turning it on and off. Alright, so before I turn this on, I want to do one last voltage and polarity check. So on the battery side, I've got 54.3 volts, correct polarity. And on the charger side, 58.7 volts and correct polarity. So we're good to go ahead and turn it on. So now I can take a look at my BMS here, and I see it's charging at 14.7 amps and 811 watts. So let's just take a look at what the balancing configuration is for this. So I'm going to click on Menu, go to Hardware, Cellmon. So it's set to begin bypass at 3.50. I think I'm going to increase that to 3.60. So I'm going to click Edit, and I'm going to have to change this to Custom. Change this to 3.60 and go back to Menu and Chart. Alright, so I've got the batteries near perfectly balanced now. I ended up using this iCharger X6 to boost up those two battery packs that were lower than the rest. And that brings me to one key piece of information I should have mentioned earlier but hadn't, and that is that this Batrium BMS is not a FET-based BMS. That means there are no transistors. The power going to and from this battery is not going through this BMS, so there are no transistors in this BMS that can turn the power on and off. this BMS cannot communicate with this power supply. So if I would have left this power supply on, with those two groupings so low compared to the rest, I would have ended up overcharging some of the other cells, which would have been very bad. The reason why it works that I'm able to use this is because I already balanced my cells ahead of time and they were already mostly balanced with the exception of those two. So if anybody else is watching this and looking to balance their cells, one way you could do it is to either parallel them ahead of time and balance them like I did, or you could take like a relay or a contactor off of this power supply. That way your BMS is able to turn this power supply on and off as it needs. You know, if your cells are not already pre-balanced manually, I certainly would not connect a power supply that your BMS cannot turn on and off. That's a very important safety point to mention. Alright guys, so now I have the BMS configured to begin balancing at 3.65 volts. So what I'm doing is I'm just allowing the charger to float the batteries at full charge here. And you'll see it keeps flipping between odds and evens with the balancing current. It's approximately, 680 milliamps of balancing current. I know a lot of you guys are probably thinking you would never float lithium iron phosphate batteries. In fact, once this build is complete, I would never even charge them up to 3.65 volts. However, for the initial commissioning process here, it's important to me to make sure that these are completely balanced. So I'm just going to let these float for a few hours like this, and hopefully we'll see this graph even out a lot more here, especially cell number 11 that still looks a little low, sitting at 3.59 volts. As you can see, the charge is only putting in between 0.3 and 0.5 amps. Alright guys, so I've got these batteries balanced very well. They're all within 0.03 volts of each other. So what I've done is I've connected my Sun Gold Power 6000 watt inverter here. And I'm just going to run a pair of space heaters and hopefully put a 3000 watt load on these batteries. So I'm going to go ahead and turn the inverter on now. You can see it starting up there. And at idle we can see it's pulling 115 watts from the battery bank. And with both of those space heaters on, we're around 57 amps or 3100 watts there. And you can see how quickly the voltage drops per cell on lithium iron phosphate as soon as the load's applied. There's very little stored energy around the top charge voltage there, so we're just going to leave this run until one of the cells hits the low cutoff voltage of 2.5 volts, and we'll see what our capacity is. Alright, so around 3 volts is where the cells really begin to deviate more. Above 3 volts there was a spread of 0.02 volts, then as soon as they dropped below 3 volts it widened to 0.05 volts. As the first cell approached 2.65 volts, the spread widened to 0.16 volts and then ended up at 0.26 volts once the first cell reached 2.5 volts, which was the load disconnect as specified by the datasheet. The test concluded with a final capacity of 567 amp hours, or 101.5% of their rated capacity. That was fantastic. I'm very excited to see these cells test so well. I know there was a lot of questions because I did not individually test the cells originally, but yeah, they all seem to work exactly as described. They're perfect. Throughout the test, I did put the FLIR thermal camera on these batteries, you know, just to see where if there's any heat generated anywhere or whatnot, and grab most of the bus bars, and I didn't see any heat anywhere other than the 6-gauge wire that was coming off, so I was very satisfied with that. Keep in mind this test was only done around a 0.12 C rate test, and these batteries are rated for around a 1 C rate charge and discharge. And I did the test around 3000 watts there because that's a fairly typical load I expect to see these batteries at once they're in service. In fact, that's probably on the higher end. The load's going to be significantly lower. I'm not going to be pulling 3000 watts from one battery bank of multiple battery banks at a time. I do expect these batteries to last a very long time, and hopefully we see that throughout the next couple of years. Now, a few months ago I did order 32 more of these EVE 280 amp hour batteries. However, after a couple weeks, Shenzhen Basin did cancel my order and let me know they were out of stock. And they did get stock in a little bit later, but the price had gone up, and you know, I just didn't want to purchase any more at the new price. So I did order some new cells for the second battery bank, and they are here. I'm not going to spoil what they are just yet, but they will be in upcoming videos very soon. So as usual, I'd love to know what you guys think of this test and how the results turned out. Please let me know in the comments below. Hit that like button before you go, and thank you very much for watching.